All right, so listen up for a sec. We have Trevor here who is going to give you a little like 2-minute thing on something coming up that you should think about attending, especially if you don't like the way grades are done in your computer science classes. So Trevor, over to you.
This is very quick. If you think grading takes a long time in your computer science classes, or if you're thinking about continuing computer science classes, you'll find they take a really long time. So Professor Norman Ramsey is hosting a workshop on Wednesday to help come up with ideas on how to grade quicker or focus on different areas that you want to see feedback on in different areas of your project. So yeah, that's Wednesday at noon. We have pizza. If you don't get emails from ComSci Exchange, we hold more EncyCled. You could join our group on Facebook, and we'll post stuff there. Are there any questions on this?
This is for faculty to get better at grading your stuff, basically. Like we sometimes take too long, and we don't necessarily give you the feedback you want. So this is for your opportunity to put your feedback in on how we can make it better. Anybody have any questions for Trevor?
Is it Halligan?
Yes, Halligan 111A. So that's one at the very end.
Cool.
All right.
All right, thanks, Trevor. See you. All right, so we had a homework assignment due yesterday. Hope you guys did all right on it. Yeah, and my name's in the paper today. My picture's in the paper today too, if you haven't seen that. It's funny. Somebody emailed me and said, "Hey, you're a new professor. Want to ask you these questions?" And they do this big long interview, and then I get like one sentence and a picture, so or 2 sentences and a picture, whatever. But it was very nice of them to do. Okay, so we had a homework assignment due yesterday. If you haven't, for some reason, finished it, or you weren't happy, or whatever, and you've got some, reason, whatever, as usual, email me, and we can work something out as far as getting it submitted in the next day or so, or the time frame based on your particular situation. A number of people that I talked to yesterday and over the last few days about the assignments found that some of their sorts, which maybe should have been fast, turned out to be somewhat slow, like quick sort. Anybody have a quick sort that was like really slow in the end? None of you? A whole bunch of people did in the other class, so I don't know what happened. But if you did have a sort that was somewhat slower than you expected, there could have been a lot of reasons for that, right? It might not have been as finely tuned as it could have been. You might have been going one or two over on each of your elements, and that could like degrade the whole process. Or just the recursive nature of quicksort sometimes, if you end up doing like individual elements and having to recurse through every individual element, sometimes that takes longer. So don't be worried about that. As far as the actual grading goes, we are not going to be grading on time. We will time all of yours for to kind of see how you were doing, but we won't actually grade based on like how long it took to do the sorts. I saw a number of people did quicksort. Great. That was definitely one of the trickier ones in the sense of like making it all work correctly. Merge sort was another one that was kind of tricky. A bunch of people did radix sort, so that was kind of fun to see. I know some people had a little trouble doing it, and it took a little longer than you might have hoped, but I hope the payoff was good in the sense that you actually got things sorted. We'll try to have those graded fairly soon, but here's how we're actually going to do the grading. I think I mentioned this on like the first or second day of class. I think we're going to grade this one using the in-person grading, especially because you had a big README file, and we want you to have an opportunity to say, hey, this is what I did, this is how I did it, these are the trade-offs I made, these are maybe the decisions that I made, or look, I just copied the algorithm and like made it into C++ or whatever, right? So you'll have to describe that, and I think you'll get a kind of instant feedback from the TAs who are helping look over the homework. And bring a 20 and like maybe the TAs. No, I'm just kidding, just kidding. The TAs have much more like integrity than that, I'm sure. Anyway, so that's about it for that homework assignment. The next homework assignment is going to be, I'm going to post it on Wednesday. It will actually be our last one, and it'll be about probably a 2-week assignment, and it's going to test kind of your ability to put a lot of this together. And I would suggest paying attention, say today, and maybe the previous class. If you didn't come to class, watch the video, because you may want to use hashing for this next assignment. Okay? Questions on the homeworks or anything else before we begin? Lydia?
Can you just like send out or like post on a lecture slide somewhere like a working
The explicit algorithm. Sure, I'll put that together. Could you email me and I'll remember to do that? Yeah. Yeah, it is a little tricky, and I can see, you might want to see a specific example. Sure. Okay. Other questions? Yes.
I had an issue where the random, I think it was 100,000 text file just blank.
The random 100,000 text file was blank. I wonder if you had your caret the wrong way, like the less than or equal to one you tried it once.
No, I opened it up in Emacs. It was blank.
Really? Oh. Well, I'm not sure why. Yeah, just copy the individual file. So you can copy the individual file. If you want to test it again, let me know. We'll get it for you. But you can copy the individual file. Yeah, good. Anything else? All right, awesome. So here's what we're going to do today. I'm going to show you a UNIX tip of the day, which is we've kind of talked a little bit about it before. It's called piping, and it's with this pipe character, which happens to be, I think, shift / on your keyboard. And it's kind of an important development that came from UNIX itself, which is kind of neat. Then we'll go into hashing part 2. And the hashing part 2 is what this week's lab is all based on. Okay, it's collision. It's dealing with collisions in different ways. Okay, we already saw one method, and then we're going to talk about a couple more. And then we're going to talk a little bit about, just brush on load factor again as far as collisions go. Then talk about these things called perfect hash functions, which are, in some cases, you can make. And then we're going to go into this thing called cryptographic hashing, which is kind of fun, new stuff. And we're going to talk about whether hash functions should ever be slow or not. And in some cases, we'll find out that maybe they should. OK? All right. Let's see. UNIX tip of the day, piping with the pipe character. OK, so UNIX, I don't know if you guys know this, but UNIX was actually created in like the 1970s. A place called AT&T Bell Labs, which was in those days like the premier non-government lab to go to. These days, it's probably lost a little of its cachet, but in terms of the place to like do real research, that was the place. Lots of physics came out of there, lots of computer science, lots of good stuff. And one of the things that came out was UNIX, and the people that invented it came up with this idea to have piping of various data between programs. Okay, and it's kind of cool because I like to call it one of the killer features of UNIX. And what it allowed for was your programs to be relatively modular. Like, in fact, a program does one thing and does it really well. Okay, so you might have a sorting program that does sorts. And you might have the list the directory, which just lists the directories and that sort of thing. And each program has its own little thing. It's just like when we talk about our functions. You know how we make you do a limit of 31 lines, and it's kind of annoying, especially if you did shell sort and tried to make it under 31 lines, right? But if you modularize your program, it makes it easier to understand each individual little bit. So it's kind of the same thing here. In UNIX, you can create little tiny programs that will allow input one way and output the other way, and you can make them do that to each other. So it's kind of neat. We've already seen this to some extent, the little less than and greater than characters, using to pipe into files and from files. Okay, that's what we did for a lot of our assignments. What we can do with the pipe character is actually move the data from one file to the next, to the next, to the next, for as many files as you want, instead of stopping each time to make them go out to a file. So you could do like a program name, have it go out to a temporary file, and then have the temporary file go into your next program. This like skips that step. Okay? Not only does it skip that step, but the programs actually run at the same time. So both programs start running. The second one waits for the output of the first one, which is getting input from wherever it's getting input. And they run at the same time, so it actually speeds up the process a little bit too. So it's kind of neat. Okay? All right. So here's the examples. So let's say you want to list all the files in your folder, like some folder you're in, right? You can type ls-a1. In fact, I'll show you that. All right. ls-a1 gives you a list of your files, which makes sense. And in fact, this actually lists all the files in here, including the little dot and dot dot, which means the current directory you're in and the previous directory you're in. But maybe you don't want those, because those are they're not extra directories. They're just kind of saying, hey, you've got these other two kind of fake directories in there that point to other places. So what you can do is you can say, all right, let's do ls-a1 pipe through this tail program, which says, give me all the end lines of some output or input that I've given you. And in fact, there's a flag that's -n, and then you do a plus the number of lines you want to start it on. So I want to give the whole file except for the first 2 lines. I'm going to do tail -n plus 3, saying start the output on the 3rd line. And when you do that, you can pipe through tail -n plus 3, okay? And it will give you it will take out the first 2 lines starting there. So there's all your files. So far, so good? Okay. You can continue this. You can pipe through as many times as you want, right? Let's say we want to count all the files in our directory. Well, there's probably an ls flag that does that, but let's say there isn't, right? ls-a1 through tail-n plus 3, and then pipe through this thing called word count, which is just a program that counts the letters, or the letters, words, and lines, I guess. Lines, characters, and words. That's it. Lines, characters, and words. And if we want to count just the number of lines, we do -l. And oops, that will, let's see, there we go. Pipe that through wc-l, and it says 22. So there's the number of files you have in there. Okay, and you can keep doing this for as many pipes as you want. And it just allows you to kind of streamline this stuff around and manipulate your data. It's actually a pretty good video online about one of the inventors of UNIX. This guy named, I think his name was Ken Thompson, who shows people, like this is in the 70s, shows people how to do this. And he formats all this text, and it ends up doing cool things. So that's that. Questions on piping? One of UNIX's killer functions. Nope. All right. OK, let's see. Oh, I didn't show the other class my lol code thing, but I wanted to show you guys. So there's this class of programming languages like this one, which are considered esoteric programming languages, right? There's one that there's some that are basically made to make you frustrated, like certain languages that are like completely frustrating to build. There's a whole language called white space, which actually the program is written in the white space. Like however many spaces you have, like that's how you write the program. So you can actually write anything, and then in that language, it's a different program. It's whatever, you know. So there's that. There's another one which I saw earlier today. I was looking through languages, and is this it? No, where'd it go? Oh no, hope I didn't lose it. Hold on. Let's see, esoteric language programming languages. Let's see, esoteric programming languages. Here we go. There's a whole wiki page on it. But I think one of the interesting ones, this one. OK, see these colors here? You can see this over here. These colors, like this, like that's a hello world program, right? Like that program itself like prints out hello world or whatever in whatever. It's based on the colors of the little blocks. That's how the programming language works. So kind of cool, like totally out there, like not language based, but color based. Odd. But anyway, fun stuff if you want to get into like various programming languages. There's also a Shakespeare language, which Shakespeare is designed to make programs look like Shakespearean plays. For example, the following statement declares a point in the program which can be reached via a go-to type statement. Act 1, Hamlet's insults and flattery. That's part of the programming language. So anyway, all right. So esoteric languages. OK, let's get back into hashing. Now, I apologize about the linked lists here looking like all scrunched up. This is an artifact of me having to squish everything so it fits in the top. So we have the board here. So I just kind of scrunched it up. But anyway, this is actually a linked list and it's actually, in some sense, it's linked lists don't go down, right? They go in different places in memory and whatever. Anyway, remember when we talked about hash tables last week, we started talking about, or on Monday, last Wednesday, we started talking about the way one way we deal with hash collisions called chaining. Okay, when you chain values together at a bucket where they all hash together. Okay, and this is one of the things you're going to have to program in this week's lab. Okay, Jason, it's not so bad, is it? Not too bad. And what you have to do is, when you go to a location, if there's no value there, you can have the first node in your linked list be a node, right? Which is the key and value that you're worried about. And then if not, you have to just start a little linked list. Okay? And that linked list points you to all the different locations that are in your hash table. Question. If we're going to do this chaining here, is it better to put the next node at the top or at the bottom? Or doesn't it matter? What do you think? Yeah, what do you think, Dylan?
Well, if we're adding a lot of elements,
If you're adding a lot of elements,
then it'd be easier to put it at the top, right?
it'd be easier to put at the top if you're adding a lot of them, right? Because you don't have to actually walk down the list. If you know that it's going to hash there, you can do that. There's problems with that if it happens to already be somewhere else. The key's already in your linked list, right? Then you might need to walk through it. But otherwise, yeah, putting it at the middle is there, or at the beginning is easiest in terms of time, so you don't have to walk through each chain. But as with all these things, if you're dealing with a linked list or anything else, you have to think about what's my usage case. Like, what am I doing this for? Some cases, maybe it turns out that you add a lot of things to your hash table, but then you're going to look for the objects in the reverse order or something weird like that, right? Well, then maybe you'll want to put it at the end so that lookup's a little quicker for the elements you're looking for more. It all depends on your use case. But the bottom line is here, this is one way to deal with this collisions. Okay? What is a good thing about this? Let's say my table was 10 elements long, or 1, 2, 3, 4, 5, 6, 7 elements long. And I have a million things that I want to hash. What's good about this method? We know what's bad about it, right? A lot of things would collide and the linked list would get really big. But what's good about this method? Anything in particular? Yeah?
Super fast to store things and store as many things as you want.
Super fast to store things, OK. And you store as many as you want. Yes, why can you store as many as you want? Yeah, each box has a linked list that can store as many as you want. In other words, you don't have to change the size of this array, right? That's a benefit to this. Okay, that's one of the benefits to chaining. Okay, all right. One way to deal with collisions is chaining, blah, 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 elements collide. Okay. So we know that if elements do collide, the chains decrease performance. That goes without saying, because the more linked list you have, right, the better, the longer it's going to take to do the searching. You do have to add this other structure. Like, you've got a hash table and linked lists. That's a little odd. I mean, in the sense that you've got two structures kind of competing or both in one data structure. I mean, it's not odd. It's just the way we do it. But it does complicate it slightly. I mean, you have to have nodes, and you have to know how to walk a linked list and all that. And so in that case, it's not necessarily the best way we want to do it. Okay. So there are other ways to do these things. Okay. Let's try to think of a couple here. Let's say that we want to hash something, and it's going to go into this first bucket. And Jason, you're not allowed to answer this because you're in lab already. All right. Let's say that we've got an array here, and we hash something, and it's going to go into that bucket, but that bucket's filled. What options do we have? What's that? It's filled. Like, so let's say there's already an element there, and then we try to hash something else, and we find that there's already an element there. Before we would chain it. Now we're not going to chain it. What other options do we have? Allie?
Put it in the next closest central location.
Yeah, I like that idea. Put it in the next closest location. So if this one's filled, look at this one. Oh, it's filled. Look at this one. Hey, it's not filled anymore. So let's put the value there. That's very good, OK? That's actually perfect. Yes, Margaret, and then James?
I thought the point of hash was that you could, by the index value, know exactly what's there.
That is right. The point is that by the index value, you could do that. So
That's the problem. You can't just put the next closest because there's no way of getting that.
you can't put it in the next value. Right. We have to figure out how to get to that value, right? So here's the problem, right? The problem is you're going to have collisions, right? We saw that whole birthday problem issue where you're going to have some sort of collision, right? Unless you have a perfect hash, which we'll get to later. But in general, you're going to have a collision. So we have to be able to deal with the fact that it's not in the bucket it should be in. So we'll figure out how to do that. But that's what we have to figure out still, right?
I thought that's what chaining was.
Chaining actually says it's still in the same bucket. Now we're saying we're not going to have new buckets. We're not going to have any linked lists. We're going to just put it in some other bucket. We just have to be able to find it. So that's exactly what we have to do. Yeah, James.
So couldn't you write an algorithm that says if you go to that index,
There you go.
Add one, like you know, depending on where
Yeah, it's exactly the same algorithm as if you're putting it in, except now you're doing the search. So I don't know if you heard what James was saying, but he said, look, all right, fine, we're looking for it. In fact, I think this might be like 2 slides from now. But look, you try to look for it, and it's not here. Well, then you go to the next one and see if it's that one. And then you go to the next one and see if it's that one. When do you stop looking? When you find it, or? Reach the end. You just reach an empty one, right? When you reach an empty one, well, it's not filled, and it would have been filled had it been there. So it's got it. So because it's empty, you're not there. So that's a good way to go actually do the search for it. OK? All right. Any other ideas? That's a good idea. In fact, that's the next one we're going to talk about. But any other ideas before we go on how we might try to arrange this so that we go and just find one of those other empty buckets? Yeah, Dylan?
You said our hash functions have to be deterministic, right?
Hash functions have to be deterministic.
Can they have ordinals? So can we have like an optimal decision? And then if that doesn't work, so for every hash, right, we take the value, we put it in the hash function, we get an output. If that output's occupied, can we have alternative outputs?
Can you have another hash function, let's say?
Yeah.
Sure. That's actually a very good one. You can have what we call a double hash function. First you hash it, and it might go here. Then you say, oops, we've got one. Let's hash it against another hash function, right? And maybe the original value, too, so to keep kind of the random nature. I'll do the original value, and then that'll jump to somewhere else, and we hope that one's empty. And then, as you'll see in the lab, we'll get into what you have to do with that case, and I'll talk about it in a minute. But yeah, that's very good. OK? All right. Yeah, James?
Could you, kind of like chaining, but instead you point it to an array of like, instead of being a linked list, you could just point it to an array.
Instead of a linked list, you could point it to an array. That would still be considered chaining. Okay. Yeah. In fact, it would be a different type of chaining, but yeah, it would be this. So here's what we decided, right? This is what we could try to hash to the first one, and we would look at that one and check the next one. And then check the next neighbor, and then we can find where the location is. This is actually called linear probing. In other words, you're probing one value, then the next, then the next, then the next, then the next. OK, so this is what this one's called, and you end up finding the location. This is called an open addressing way to do this. It's kind of an odd name, but it's called open addressing, meaning find an open location to put the value. Okay? And of course, if you reach the end, let's say you try to put it here, you would, and this was the end of the table, you would go over to the other side, you would do a mod function until you find the right one. Okay? What might be a problem with this? There's a couple different issues we might have to deal with this. There's a glaring issue, which we definitely have to figure out. But there's another issue that might be a little trickier. Sam, what do you think?
Don't we still have to keep the original value?
You do have to keep the keys. Either way, you do have to keep the keys and the values, because when you're searching, you have to be able to check against the key. So yes. Yep. Wouldn't the size get pretty large? Now, are we changing the size of the array? We're modding it when we get to the end. So this could be the whole array. So let's say we put another one in. It goes here. And then we wrap around and go, oh, can't go there. It goes here. You see what I mean? So actually, in fact, we're not adding. We're doing what? What's the kind of the benefit here? It saves space in that we are going to fill the entire thing before we have to do anything else. So what does that lead to your next question? Yeah?
Well, if the array is filled, where do you put
Yeah, if your array is filled, what are you doing? Yeah, in fact, if the entire thing was filled, our program would just keep looping forever, right? Because it would go, nope, filled, 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 filled. Oh, let's go back around. Filled, 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 right? And then you'd be done, right? You'd have to either keep a count of it. You'd probably have to keep a count of the number of things. Or you'd have to worry about the load factor, which we'll get to in a few slides here. Okay? There is another method here. There's one other little issue here about if you don't have the best hash function in the world, okay? And you tend to cluster a lot of locations, like cluster a lot of buckets near each other that are going to be filled. This tends to break down a little bit, because let's say there's a whole bunch in a row that are filled, and you're always hashing to one that's like here. You got to check this one, then 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 this one, and then put it in. And then same thing. Da, 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 da. There's another solution called quadratic probing that is on, there we go, called quadratic probing, which adds an arbitrary quadratic polynomial until an open spot is found. In other words, you're going to try to fill it here. And notice this, by the way. Our quadratic function is going to be called the attempt that we're making. starting with 0. Okay, so the first attempt is actually 0, the 0th attempt. And if and 0 squared is going to be 0, so hash code plus 0 would say it's supposed to go there. And then you say, oh, well, it filled. So then we're going to try the next one, which is going to be hash code plus 1 squared. Happens to be 1, so it's also going to try to go there. Not a very good not a very good quadratic function. But the next one, it'll say, OK, hash code plus 2 squared. Instead of doing all these ones, it'll jump over and put it there. And you can see if there's clusters of them, it'll actually spread out the number of locations relatively quickly. It'll be better for spreading out. OK? All right. Now, back to this one. If we want to actually, if we want to actually search for the value, you do have to go through the whole function again as you find that they're not there. So we mentioned this already. If you're going to hash key 3, look where it's supposed to go, then apply your function, in this case linear. Look here, it's not there. Look there, it is there. And if it's empty, not there. Okay. All other questions on that? No? OK. All right, so we had quadratic probing and linear probing. And we did mention this, right? If the table is full, or you can't find another entry, you've got to be a little careful. If you're doing it linearly, you're definitely going to hit every bucket. That makes sense, right? If you're doing this quadratic one, you may pick a function that skips over values and gets back to the one it started with, and then actually doesn't go through and find another empty bucket for a while. So you have to be a little careful with that, right? But in most cases, linear works fairly well. Quadratic's a little bit better for, as I said, for when things are bunched up. Okay? But if we fill the table, then we're in trouble, right? Or we have to deal with it. But we're in trouble in the sense of it's going to be filled up. And if we use a bad function to try to find the next one, we may actually break the table. It'll loop forever or crash or whatever. So we have to keep an eye on this load factor. Now, remember what the load factor is, right? Load factor is simply the number of keys that you're going to store divided by the total number of buckets. And what you want to do is you want to keep that, for open addressing, you want to keep that value right around 0.8 if you can. Try not to go above that, because if you start going above that, then you get to this case where it's slow to find and you may actually break it. Okay? So try to keep the load factor somewhat low. Okay? But then sometimes it might actually increase. So if the load factor gets above the value that you want, let's say 0.8, how do we actually increase the table size? Okay? So you've got a table, right? I'll write it down. You've got a table like this. Okay? And it's got values in it 3, 7, 22, 4, 9, and 6, right? OK. How are we going to expand that table? How did we do it it was easy for regular dynamic arrays, right? Right? You just double it, you copy all the elements over and do that. It was slightly harder for, one second, it was slightly harder for when we did queues, right? Circular queues. Remember we did that lab on circular queues where you had to make sure you knew where the front and the back were and move the values appropriately so that the queue function still worked with front and back? That was kind of a tricky one. OK, so the idea here is, it's terrible. Hang on. Here we go. The idea here is make the table bigger, right, and somehow figure out how to do it. Ethan, you were going to say?
Expansion should be the same as the dynamic array, except instead of the step where you copy everything from the old array to the new array, you pass it through the hash function to figure out where to insert, but the hash function has to know the new size. So it'll have to be different.
Yeah, so what Ethan's saying is you have to actually go ahead and rehash all of your keys, right? Why do you have to do that? Because let's say that the hash function for this was some function like, I don't know, 2x plus 1, and the x is being your key. And let's say that the 3 ended up, or the 22 ended up going there in this one. Remember, we have to mod it by 2, 3, 4, 5, 6, right? We have to mod it by 6 to actually put it in the right place in the table, right? Well, in the new table, is this 2x plus 1 mod 6 going to give you the same location for 22? Possibly, probably not, right? So it's the idea that if you have a new bigger hash table, your hash function will change to some extent because you're modding it by a bigger number now, and that will change where the locations of all those numbers are going to go. If you try to just copy it down here, you'd never be able to find them again because you have no idea where they are, right? So yes, so indeed, if you're going to do it this way, you have to rehash everything, which is kind of slow, right? It's kind of slow to do that. I mean, we hope that our hash function is fast. But rehashing it, meaning putting every key back through the hash function and then putting it in the right place in the table, well, that does take some time. Okay? And sometimes it takes enough time to really slow your program down, which is not really that great. Dylan?
What if we had a way of anticipating that we were going to have to do that, if we knew we were dealing with a big data set?
Yeah.
What if we were actually hashing it twice every time that we were putting it in? One on the main array that we wanted to, but then keep the second one somewhere else in memory, so that when we did have to rehash it, create a new bigger table.
So the idea is why not have two tables and just kind of keep the other one in reserve? Yeah. Why have this one at all? Okay. Like, I mean, there's either it's the same lookup time, right? I mean, this one might give it slightly better cache. Like, it might work with the caches a little better because the values are closer together. So maybe, but yeah, I don't think you necessarily want to do that because you'd waste a lot of memory doing that. But you never know. That's not a bad idea. You might have a use case for that. OK. Anybody in here program in Java? A couple people program in Java. So Java is one of those languages. It's very similar to C++ in the sense that it's got objects and it's got arrays and it's got, it's very C++-like in some sense. And it's got constructors and all that. But what you don't have to do in Java is you don't have to delete objects. Right? You actually can create as many objects as you want, and you never have to worry about deleting them. Because Java has this thing built in called garbage collection. Right? And it's actually a really good name, because what it means is if you stop using an object, right, and it knows that because it's keeping track of when you're going to, if you're going to access an object again. In many cases, you can know whether or not you're going to access this or not. If the compiler or runtime or whatever decides that you aren't going to use a certain value anymore, it will put it down to a place where it's going to get deleted. Like it's going to put it in some other list that says delete this eventually. And that eventually is not up to you, right? You don't get to decide when the garbage collector actually runs. Which means that some people's complaints about languages like Java are that they're slow at times. Because you can, and you don't know when they're going to be slow. So it's not like you can predict, oh, it's going to be slow at this time, because you don't have any control over that. In some sense, Java does something very similar with their hash table implementation. When their hash table gets to a load factor of about 0.8, it just says, stop, I'm taking the time to rechange this. I mean, your programs do the same thing when they expand dynamic arrays and such. But if you're dealing with something like a hash table and has 1 billion elements in it, there might be a time when it has to rehash all 1 billion elements. And that's going to slow your program down to a crawl. Like it's actually going to just not do anything while it's doing that. I mean, it might do it in the background somehow, but it's going to make it really slow. So there's trade-offs to different languages. Java happens to be one that does that. In fact, I believe even if you use the standard library in C++ to do hashes, it'll also do that. So just to be a little wary of that. If you're using some of these structures, they may have to do expensive things like that every so often. Okay. All right. So we mentioned all these things. You can't simply create a new dynamic array. You need to rehash all the keys. And there is one other solution. This is trickier. If you can figure out a way, right, to have your function such that it doesn't really depend on the modulus as much. Like now, you can't do that for every value. That's not possible. But for many values, you wouldn't necessarily have to rehash them. It's called consistent hashing, which means that it hashes most of the same keys to the same value. Okay, it's tricky to do. It's tricky to come up with those things. But there are some possibilities for coming up with consistent hashes which allow you to put the value or not rehash everybody. Okay, so some ways you can do that. Sometimes you can do that. Okay, question on resizing a dynamic array? Or a hash table, rather? No. Yeah?
So with consistent hashing, would you be moving everything into a new array?
With consistent hashing, you would still move it into a new array. You just wouldn't have to apply the hash function, or at least you wouldn't have to I'm not exactly sure how they implement some of these consistent hashes, but the idea is don't rehash them, right? Move them, but don't rehash them. Now, in some sense, I think you'd have to rehash them to figure out if they're consistent, but there might be some, if it happens to meet some requirements, it won't need to be rehashed. Yeah. Okay, question?
So it's not so much that like the hash is consistent as like the lookup is consistent?
It's not so much the hash is consistent, but the lookup is consistent. I think you could think of it that way. Yeah, you could think of it that way. You just have to be able to find it again, which is the tricky part. Yeah, good. OK. All right. So yeah, we already talked about this. Search, if we try to, oh no, sorry, we did not talk about this. If you want to remove an element from one of these open addressing tables, let's say we want to go and delete this key right here. OK? Why might that break other keys? Any ideas? Hey, Sam?
Yeah, if you remove key 2 and look for key 3, you're going to get to key 1, see a blank, and then stop looking.
Yeah, if you were to look for key 3 in this case, right, you deleted key 1 and you made it empty, then you'd stop when you got there when you did the look. You'd say, oh, it's not in the key 3 is not in the table because it's an empty box. Is that what you're going to say, Ali? Yeah, same thing, right? So what can we do to stop that? Like, when we delete key 1, what do we really want to do?
Just change it to like a blank value that doesn't necessarily.
Change it to a blank value. In other words, mark it as being deleted, right? So we can't do that because that's bad, because key 3 and key 2 would actually be gone, right? Because they both hash the same thing. And you'd look for key 3 and then blah, 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 right? So what we can do is we can mark it as deleted. Right? And then when we're looking for key 3, we get to this one and we say, oh, it's not only not there, but something was here, so we better look at the next location in our linear probing or our quadratic probing or our double function and whatever. Yeah?
Wouldn't marking have issues if you have to do it a lot? As in, like, if the whole thing's marked, then you can tell the difference either.
Yeah, if the whole thing's marked, then you're in trouble. However, let's say that the next value you hash was supposed to go into the one that's marked deleted. What can you do? You can what? You can put it into the deleted one. So the deleted ones are only going to be deleted for a fixed amount, a relatively short amount of time if a lot of things are going into that bucket, right? Now, the other idea is, there's another idea where you can move, in fact, I think this is the next slide. You can move key 3 into here. Like if you do a search for key 3, you could then bump it into here. You would have to be really careful with that you also mark this one as deleted, right? And so, like for instance, you're finding key 3, not here, it's here. And then what we could do is actually move key 3 over here, mark this one as deleted. I think on the next thing I have it as empty. It should be deleted. And then you won't have to search through a deleted one. Next time you look for key 3, you'll find it right there. And it'll recompress the function a little bit, which is kind of what you want. Yeah?
Do you find the last key that?
Yeah, that's a good question. I mean, could you go and find the last key? Well, I'm not sure you could. Because, well, I guess you could. You would just search until you found a blank in the next available location. Yeah, so in some sense, I guess you could. You could find the next one, although you're not necessarily sure that that one should have hashed into that location. Right? OK, so watch. Let's say that let's say this was filled, and I was looking for 3. Right? Well, let's see. If the only way is the next one would have to be empty. But let's say there's not an empty one in the next one. Like I'm looking for filled, key 3. This one wasn't empty. I mean, you'd have to go, and when you find an empty one, it might be part of the one before it, not part of the original. So in other words, you can't go and well, right. I mean, you would.
It's not that it's empty. You just find the one that's either empty or one that doesn't hash to.
Right, but then you would have to rehash and figure out if it was supposed to go in the original deleted bucket. I mean, that's the issue, I guess. Yeah, it's probably not worth it. Probably just worth it to just delete it and then fill it in later with a new one, or possibly one that you find and just swap the deleted flag in that case. Okay, good. Good questions. Anybody else? No? OK. All right. So, question, is there a perfect hash function? Right? If you don't know the keys in advance, you're kind of out of luck, except in like very trivial case. Well, in the trivial cases I'm talking about, you actually would know all the keys in advance. But if you don't know what the set is that you're looking for, you're kind of out of luck, right? If we do know the set ahead of time, we can find what we call a perfect hash function, which means there will be no collisions. Okay, that's what a perfect hash function does. It says no collisions. We've actually seen one already. Remember the 2-character word hash function we used, like the last time we did when we started hashes, right? Those 2 characters, if we limit our word size to 2 characters, and they're only lowercase alphabetic characters, we know that there's a maximum of 676 locations. And when we go to a location, or when we have a word, it will always go into an empty bucket, because no other word could also go into that bucket. Okay, so that would be a perfect hash function. In fact, that would be what's on the next slide, or 2 slides away, called a next slide, I guess, minimal hash function as well. But anyway, it is not trivial to find these perfect hash functions. You can look online. There's a lot of papers. When I was doing some research on this, I found there's a lot of papers that talk about finding perfect hash functions for a set of keys. And then this paper in particular gives you a section that talks about other references which do that. So it's interesting, but it's not trivial to do. Okay, but they do exist for a set of keys. Okay? If you happen to have exactly n buckets for n keys, which was the example we used, the 2-letter words, right? This is called a minimal perfect hash function, which sounds a little odd saying a minimal perfect hash function if it's already perfect, but it means it's minimal in that it's fixed to a certain size, right? Where every key has a value. And that's even harder to achieve except in those trivial cases. But it's possible. There's other things you can look up to figure that out. Okay. Any questions on perfect hash functions? We're not going to worry, but I'm not going to test you on perfect hash functions. Just kind of know what they are. Okay. All right. The next topic we're going to go with is this idea of cryptographic hashing. Now, this is actually kind of cool stuff, I think. As I think I mentioned before, one of my jobs in the Navy was as a cryptologist, which is basically working with codes and working with encrypted messages and all that stuff. Unfortunately, the more you get promoted in the military, you end up in management positions where you're pushing around a bunch of paper, and all the fun stuff is done by the people that work for you. So that's not quite as fun. But like these days, I don't do all this fun stuff. Like some of the guys that work for me do, but I don't really do this fun stuff. But here's the way cryptographic hashing means coming up with these hash functions in order to have some sort of either security implementation or some sort of verification policy or something where you want there to be an answer that's not easy to go backwards on. I'll show you what I mean. Okay? We can have the following hash. Anybody know what this is from, this hash function is from, what string it's from? Of course you don't. That's the whole point, right? It happens, right? This hash function is what we call a cryptographic hash. And what it means is there is some string out there that, given a particular hash function, will produce this. And it would be very hard for you to do this backwards, to take this and go back to that string. This happens to be I think it's 54 characters long. It's 2 to the, sorry. I think it's 226 bits long, something like that, right? And what I actually used to hash this was the string struggle bus, right? I mean, you've heard that, right? I heard that last week, right? And this is a struggle bus. I found this little GIF online. What that refers to is how hard you'd have to work to try to get the string back here, right? Because the point of this is that you're not supposed to be able to go backwards on these functions. Okay? So cryptographic hashing is pretty cool. So we'll spend another few minutes on this. In fact, there's a whole class you could take. I don't know if they teach it here often or at all, on cryptographic methods and cryptographic hashing and so forth. So here's what a cryptographic hash is, right? It's a hash function that takes some block of data, whether it's a string or a really long, a whole file or a message you type out to someone, and it returns another string that's a fixed length long. And the important part is that any change to that original data will change the hash value in a very big way. And I used some examples last week, which I'll kind of reiterate again here. So this is the one that I used here. This is the message struggle bus, and it hashed into this value. Sometimes we call the hash the digest, okay, because it's like been digested into this other value here. But struggle bus hashes into this long value. You can't read this here, but what it says is it's like a Python little one-liner to actually turn struggle bus into this big long value. Okay, that's what we're talking about when we're doing these cryptographic hashes. Okay? You do not have to write this all down, right? You could, but you can just use the function to do it, or go online and figure it out. Okay, you don't have to write all these down either, because we're going to go through them individually. The cryptographic hashing has basically 4 tenets to them. Okay, 4 tenets. The following tenets: easy to compute the value, it's infeasible to generate the value, the message that has a given hash, infeasible to modify a message that without changing the hash, and infeasible to find 2 different messages with the same hash. What we're going to do is walk through each one of these one at a time and kind of think about why that's the case. Yeah?
Once you get out the digest, how do you put that into an array? Or
well, well, you could do it a hash table. We're not really talking about hash tables anymore, although I suppose you could use these as hash tables. Cryptographic hashes can be used in hash tables if you want. There's going to be the good thing about them. They're going to be relatively low collisions, because that's kind of the point of them, right? They're going to be relatively unique. So you could do that. Part of the problem is they're not as fast necessarily as you want them to be. You can come up with other better functions for a hash table which are faster. Now we do want them to be relatively fast. That's one of the things here. But yeah, in general, we don't need to use cryptographic hashes for them. But you could. How would you get into a table? This is just a number. So that could be. I mean, it's a 226-bit long number, right? You'd probably want to mod this, right, to fit in your table somewhere. But that would be what it was. Okay. All right. So first one. It's easy to compute the hash value for a given message. You don't want this to be a completely tedious process, except in some cases, which we'll get to in a few minutes. In general, we want cryptographic hashes to be relatively fast so that we can use them on big files, okay, or big pieces of data. Okay? You want to encrypt a lot of messages. You're going to want the hash function to be very fast. Okay? You also want to be fast to be able to verify messages, which we'll talk about in a minute. Okay? All right. The next one. It's infeasible to generate a message that has a given hash. In other words, let's say you have your password. Okay? You come up with a password hash. You don't want somebody who gets that hash to be able to go and figure out your password. Right? You don't want to be able to go backwards. Some hash functions aren't necessarily only forward functions. In other words, you can generally figure out maybe from the value if you want to go backwards. The 2-letter word example. If you know the position in the hash table, you can figure out the 2-letter word. You don't even need to store the word. Right? Cryptographic hashes, though, you do want them to be one way. You don't want to be able to go backwards. Okay? You can also think of this because let's say you had somebody who wanted to be deceptive, and you have a hash, and they say, here's the message I used to create this hash. But it wasn't. It was some other message. You don't want 2 hashes to collide like that if you can help it. Not always possible, but if you want unique hashes. Okay? All right. It is infeasible to modify a message without changing the hash. This is another important one. And this is I think I used this example the other day, right? So let's say that Brianna has the password hello, right? And somebody else has the password HELL0, right? Like Yuval has the password HELL0. If I find Brianna, is that your password? That is your password. OK, change it. Then if I find Brianna's password, I don't want to look at the hash and say, oh, it's really close to like this hash. So or rather, if I know her password, I don't want to be able to say, oh, let's change it a little bit and see and get a hash that's very close. For instance, if you have the message struggle bus, which had the digester hash this, if you change it to struggle bub, right, BUB, the hash is completely different, right? I mean, some of those overlap just because there's 54 of them. They're going to overlap. But there's no, like, you can't go from this one to this one without, if you change one letter, like there's really no difference, or no, they're not the same hash or even close to the same hash. Okay? And that's the issue with, that's one thing you want to make for a good cryptographic hash. Okay, and then finally, it's infeasible to find two different messages with the same hash. This is the collision kind of issue again, right? You're basically saying, look, collisions are going to happen, but it's make it as unlikely as possible so that two of the same message won't create the same hash. So you can't be deceptive and so on. Okay, questions on those four? Go through some examples here of what are good types of ideas with these. Okay, here's our first example. So it turns out in cryptography, we always use two characters here. We always use Alice and Bob. Not necessarily Alice in Wonderland and Sideshow Bob, but we use the names Alice and Bob. And sometimes you have Eve, who's eavesdropping on Alice and Bob, right? But sometimes Alice is good and Bob's bad and vice versa and whatever. But anyway, you use these, so you'll see these if you do any with cryptology. So let's say that Alice here is kind of a math whiz, and she says, hey Bob, I've solved some big math problem. And Bob says, really? I want to solve that same problem. And Alice is like, well, I want to prove to you that I solved it first. Right? So here's what Alice does. She writes down the solution, and then she finds the hash of that solution. And she gives the hash to Bob and says, here's the hash of my solution. And then Bob goes and he figures out the problem himself. Okay? And then he says, hey, Alice, I figured out the problem. And Alice says, good, here's how I hashed that function. Here's my password, or whatever I used to hash that function, or that solution. And she gives it to Bob, but Bob goes and hashes the solution and finds out that it ends up with the same hash that she gave him. So therefore, her solution was the solution that produced the original hash, and therefore Bob can say, oh, you did figure out the problem early, as long as it's the right solution. But the whole point is that Bob can, or Alice can prove that she was the originator of the first solution by giving him the hash, and she doesn't have to give him any other information. She doesn't have to actually provide the actual solution, okay? Because you can do it this way. Yeah.
Which Alice needs to provide the function that made the hash, and also the hash that it produced.
Yes, she needs to provide. Originally, she provides the hash, and she says, "Here's a hash." Bob goes, "Okay," and puts it aside, solves the problem himself. And then she says, "Okay," and he says, "Now I want the solution." She gives him the password and what hash function she used. Okay? Yeah, that's good. All right. So then that's one idea. Yeah.
If you know the hash function, can you then go back from the hash to the original content, or still?
That's one of our tenets of what hash function shouldn't be able to do, right? Even if you know the hash function, you shouldn't be able to go from the hash back to the original. And that's going to be really important in a couple slides when I reveal one other thing about hash functions too. Okay. All right. So let's say that, and we talked about this one the other day too, password verification. Okay. Right. So Charlie stores his password on a server, right? And if he stored the actual password, that means that the system admins have the password. Anybody who goes in and steals the password file has the password. And Charlie, while a bright guy, might use his same password for some other system, right? You don't generally want to do that, in fact. But let's say he did. Well, if you steal the password and it's in plain text, then they can go and log in other places, right? What you don't want is for that to be possible, okay? And so in this case, what you can do is we take Charlie's password and we hash it. And it becomes a hash. And you store the hash with his username. The next time he logs in, he types in his password, it gets hashed. You just compare the hashes together. And therefore, you have verified that his password is right. Now, there will be collisions, but you want to minimize collisions so that somebody else's password doesn't also match Charlie's, the hash. Now, it could be the case that whatever password you use hashes to a value that somebody else happens to also have a different password that also hashes to. What that means is that they could log in as you with their password, but the odds of two people figuring out that that's the case is very, very, very slim. Okay? It's probably true for some people, but for two people to figure out that they're the two people that match, very slim. Okay? So that's how you verify users. Okay? Good. Verify their passwords. Okay. Is there a case, and we're finally getting to this, is there a case where hashing should be slow? Any ideas based on what we were just talking about? Ethan.
If you suspect that your enemies are going to try to brute force your hashes, reverse engineer them, see what you said.
Okay, so let's parse through what you said. So you basically said if the attacker tries to brute force your hashes. What do you mean by brute force your hashes?
They know your hash by like listening to.
They know your hash. They steal the user file and has all the hashes in it. Yep, that happens, by the way, too frequently.
So what they want to do is just generate random strings and pass them into the hash function until they get one hash.
Got it. See, they don't necessarily want to generate random strings either. They want to generate, like, there's a list, by the way. You can go online. There's a list of like common passwords, right? And it's like password and 1, 2, 3, 4, 5 and I love my cat, right? And that sort of thing, right? So it's common password. They first will try the common passwords. Then they might try to do some sort of brute force where they try other permutations of common passwords. There's a whole like set of programs you can download to do that. Yeah.
So when someone steals the hashes, they can also frequently also steal the hash code. That the hash
Well, that's a good question. Yeah, in fact, that's on another slide, but I might as well talk about it now since you brought it up. Turns out that most hash functions in your code are published out in the open so that anybody can read them. Okay? And you might say, well, that seems silly. Why wouldn't you want to keep that a secret? Right? There are good reasons why not. Jason?
Isn't that how like some of the emails are monitored?
How some of the email, how the email from like the NSA?
Yeah.
No, that's not necessarily how the emails were managed. But let's think about this for a second. Okay. So, but bringing up the NSA is not a bad idea in this case, right? Let's say, okay, that the NSA says to the people who make UNIX, hey guys, we have this great hash function, okay? If you use, what you should do is you should just install it in your computer, and it's going to create all these great hashes, and it'll be very, very secure. And then you say, great, give me the source code for that. And they say, no, we'll give you the binary code for it. You don't need to worry about the source code, right? Like, in other words, they won't tell you what the algorithm is. OK, 2 issues with that. Issue number 1 would be, well, let's just say that the NSA wanted to put what we call a backdoor into the program, right? Then that means that they can like break it without worrying about all these nifty like mathematical worries about how hard it is to break these things, right? So that's one thing. You want the hash function to be open so you know there's no like hanky-panky going on, right? That's kind of the big deal, right? You want to know that the function is good. There's another reason though, okay? Let's say I said, last homework assignment for you guys is create a hash function. It's not. But let's say create a hash function, right? Well, do you think you'd create a very good one, like a cryptographic hash function? I mean, off the top of your head? I mean, I wouldn't, right? There's actually a saying in like cryptology circles which are like, don't ever create your own hash function, right? Leave it up to the experts. And there are very few experts in the world who can do this. The NSA is actually a pretty good one. And there's a bunch of researchers who their entire life has been dedicated to coming up with good cryptographic hash functions, right? Or other cryptography type functions. Why do you leave it up to the experts? Because the odds are, not being an expert, you're probably going to do something wrong. Right? I mean, that's probably, like, that's the case for a lot of things, right? But the odds are you're going to do something wrong. By having the published algorithm out there, right, you and the researchers and the NSA and everybody can test your algorithm and make sure that it's the best hash function in the world. Yes, they can figure out if there's ways to break it, but it's better to not have an obscure algorithm because you just don't know if it's going to be broken or breakable. That's part of it. The other part is, hey, if they're going to be able to steal your username file, they're probably going to be able to find that hash function anyway. So there are lots of things there. OK, but I like what you were saying, Ethan. If Bob goes and steals the usernames and hashes from Alice, right? Most good hash functions are public. And at his leisure, Bob can then create a table of known passwords. He can say, I know the hash function. I'm just going to start running passwords through this and writing down the hashes. And then if I compare the hashes, I'll figure out what some people's passwords are, or at least something that makes their hash, right? And if the password hash function was really fast, Bob can create this table really quickly, like millions of keys per second. Okay, you can check a lot of keys on today's hardware. Easy to do. Okay? So we want to avoid that. We want to make password algorithm hashing relatively slow. Ethan gave an example of a minute. You probably wouldn't necessarily want a minute. Like if you're going to type your password in and it says, OK, hold on for a minute while I set up your account, even like just because humans are like impatient, right? Probably too long. But let's say it was a second per hash, right? Like that's a long time to make a like to really crank away on a fast computer to do 1 per second. You're not going to get through very many. You're going to get through 3,600 an hour if you had a fast computer to like recreate those. That would be really slow. Okay, so that's what you kind of want to do. We call this key stretching. In other words, making the key take longer to create, or making the hash take longer to create. Okay. Well, there's of course problems with that. Computers are actually getting faster and faster at a rate that's outstripping the ability for us to come up with slow password like hashing functions, right? Password like CPUs are just getting really fast. If your password depends on how fast your computer is, we call that a CPU-bound algorithm. In other words, you have twice as fast computer, you're going to be able to do the hashes twice as fast. Well, that is outstripping the ability to make these long hash functions, as it turns out. Okay? What we can do instead is we can actually make them memory-bound, which means make them take up enough memory that you're not going to be able to utilize your cache very effectively. You're not going to be able to utilize some of these like really fast GPUs and all that. We can make them memory-bound, which is different from CPU bound because it's not about speed, it's about how much memory you have, which is growing at a slower rate in general than speed. Yeah?
Wait, so something that's memory bound, you would want to take as much?
You'd want to take it up a fair amount of memory, yeah. Like let's say to create your 54-character hash function, instead of using 100 kilobytes of memory, use like 3 megabytes of memory or something like proportionally bigger. The odds are going to be that you can't do many of those at the same time because you'll just run out of memory. So it's better that your hash function is memory bound than CPU bound in that case. Okay? So anyway, you do sometimes want these things to be slow. Password generation is a good one. Okay? So by the way, was that on the next page? We call this a, where did I put it here? Yeah, it's called a rainbow table. In other words, if you have a hash function and you start creating all these passwords that create the hashes themselves, well, you can end up getting this table that you can just compare hashes and figure out passwords really quickly. One way to combat that, right? OK, so Allie goes and uses a password that's like, cats are great or something, right? Or whatever, I don't know. No, dogs? OK, dogs, I love my dog, right? And she uses that as her password. Well, somebody who said, hey, I love my dog's a pretty common password, and uses a hash, the rainbow table to hash I love my dog, right, will be able to figure out Allie's password. Okay? You can combat that by using this thing called a salt, which means instead of just having Allie's password be I love my dog, have it be I love my dog ALI, or whatever Allie's 02, or whatever Allie's username is. Put that on and hash the whole thing. That means that if Allie uses I love my dog and Susie uses I love my dog, right, they will both have different hashes because Susie's username is different than Allie's username. So it's that you hash more than just the password in order to get the actual hash out of it. Okay? It's called salting, and it means that if I wanted to figure out Allie's password, I would have to go back and recreate my whole table based on some password ALI02, or whatever Allie's username is. And you have to do the whole password, or the whole rainbow table individually for each person. So it makes it much harder to do. Okay, question, and then question.
This question's how much harder? Because like if you have a faster computer, you can still generate.
Sure, you could still generate them, right? But the idea is, if your hashes are based on enough bits, even the fastest computer is not going to be able to do enough of them to find yours. That's kind of the idea. Now, if you know that it's going, if you know that you're going to try easy passwords first, that's fine, right? But you don't. But if you make the number of bits in the actual hash algorithm enough, it will be even infeasible to do it. That's kind of the point. Yeah. Lydia.
So like if you don't salt the hashes, are you like immediately compromised as soon as
You're
your hash table gets leaked?
You're pretty compromised, yeah. Well, for easy passwords, you're definitely compromised because people are going to build these hash tables of fairly easy passwords. Yeah. Yeah.
What are, like on actual websites, what do they normally put as a salt?
What do they normally put as a salt? Most of the time it's based on your username or whatever can define you, versus somebody else. Sometimes it's a random integer or something, but sometimes it's, and they would keep that. So let's say you log onto a website. They might say, OK, your username is going to be something. Give me your password. And then they'll take some random number that they will also keep unencrypted with your hash. And so then they can use that to encrypt it again. Okay? So it's generally something random. Now, for those of you who use the same password in each of your user accounts, stop doing that, number one. Because there are bad things, that's not a very good policy. I actually happen to kind of do a mini hash on whatever password. If I make a new password for some site, right, I base the password on something that I normally remember. I'm not going to tell you what that is, right? And then I normally use kind of a mini hash function based on the website name, like the first, third, and fifth character of the website name, right? And then some other kind of name or number that I usually use. And what it does is it actually makes my password slightly different for each site, which means that if you get the hash for one and reverse it, you'll have my password for one site, but not any of the others. So it's kind of, unfortunately, it's hard to remember them all because sometimes some websites won't let you use exclamation points and others won't let you use dollar signs, But it'll, you can do it so that it's not too hard to remember and it's safe enough. And by the way, the best thing you can do to make your password secure is make it a long phrase. Something that's nice and long and some sort of phrase that only you know. That's probably the best way to do it. Because if you make it short, it's easy to hash lots of short passwords. It's not easy to hash lots of big, long things. There's a good XKCD comic about that. Yeah?
Well, I know that sometimes when you try to log into your bank account or Google something with a new computer,
Yes.
it will recognize that it's a new computer and ask you to do additional safety words.
Yeah, that's good too.
How do they combine?
How do they combine the additional safety words? It's probably they probably encrypt you say, OK, so it says, what's your mother's maiden name? And they encrypt that using their own internal methods. And then when they think it's you, they say, what's your mother's maiden name? And then you tell them that, and it
My question is, where do they connect the computer that you usually
Oh, where do they connect the computer? So you ever heard of cookies?
Yeah.
Like not the type you eat, the type that are on your computer? That's generally how they do it. So if you log into Gmail, it saves 10 cookies to your computer, and one says who you are and the last time you logged in and all that kind of stuff. Yeah, so that's how they do it generally. Yeah. OK, so that's where we might want hashing to be slow, and this is what you can do to start to stop the bad guys from even if they get a copy of the hash of your password. OK, all right. So another type of use for cryptographic hashing is file verification. If you've ever downloaded a file from a new program or something, right? Well, how do you know that someone hasn't installed malware in that program, right? How do you know? If you trust the company it comes from, let's say you use the Firefox browser, right? Well, Mozilla, who creates Firefox, will create an installer program, right? And they say, look, we've tested this installer program. It does not have any malware. And they will hash it. And they will give you the hash based on the whole file name, or the whole file, not just the name, the actual binary file. And they publish that hash on a FTP site. Okay, you can go to this FTP site and find it. And what you can do is download the download itself, and then do your own version of the hash on it, and check it against theirs. And if it matches, then nobody's tampered with it. Okay, so it's a good way to verify that you have the right file. Okay, you can also do that to create a digital signature. And this is another one where the internet has kind of created this need for all these things, right? Digital signatures basically say, right, I am who I say I am, right? And here's how it works. There's this thing called public and private keys. Now, this is a whole nother lesson in itself, probably a whole class in public key cryptography, but it's the reason the internet works. The reason you can go to Amazon and give them your credit card and not worry about it getting stolen by someone in the middle is because they use this. Okay, they use this type of method. For verification, what it means is, okay, you can, do I put it on the next? Yeah. Alice has two keys that are her keys. One is a private key that belongs to Alice, and she's not going to share it with anybody. Okay? The other key is based on that private key, but it basically is it's based on it in such a way that you can't go from the public one to get to the private one. You can go the other way around. If you have the private one, you can create the public. If you have the public one, it's related to the private one, but you can't go back and figure out what the private one is. 2 keys. If she takes her private key, okay, and she takes it and uses it to create a hash of her message, okay, and then somebody else has her public key, they can use the public key to get back the original message, which is kind of cool. If they know that, if they trust that the public key they had came from Alice, which is another kind of whole trust issue in itself, which we could talk about. But if she trusts that, or if Bob trusts that Alice gave her her public key, gave him her public key, then he can prove that it came from her. In other words, you know that she's the one who sent it, and that means it's basically her signature, like it's signed by her. Okay, no more like, you know, actual pens or, you know, what is it, the wax implements or something, right? You don't have to do that anymore. You can then you can rehash the message and create the original, and it had to have come from her because it was from her public key. Okay, it's all very cool stuff, actually. And in fact, as I said, the whole web security is like based on these things. Okay, which means that if anybody ever does figure out how to reverse the whole public-private key thing, cryptography is like, the web is going to like collapse for a little while. Like, not necessarily a bad way, but there's going to be lots of things stolen and lots of like banking issues and all that kind of stuff. But like I said, it's a whole nother set of lessons would be on public and private key cryptography. Okay, it's fun stuff though. Okay, questions on this stuff? Okay, I think that's about all I had here. Yeah, there's some more references here. Today's and tomorrow's lab is on the original collisions. Dealing with collisions, and that's it. Questions? All right, I'll see you guys later. Yes? One sec.
You said this most recent homework will be in-person grading?
We're going to try to do in-person grading, yes.
So will you guys be notified about?
Yeah, we'll let you know when you have to go and when you have to do. Thanks. Okay, see you guys later.